Hello, welcome to week 8. We are going to go through some graph algorithms this week, similar to what we did last week with string algorithms. And like I said, we've done the general theory on algorithms, dynamic programming, greedy and all that. So now we can just look at actual algorithms, well, the more famous ones anyway. And the first one we're going to go through is the maximum flow problem, the Ford-Fulkerson method. This is probably something that you have done before in discrete math 2-7. So if you've done before, great. This is just a revision. But if you haven't, then don't worry, because I'm going to start from scratch anyway. Then we're going to be looking at shortest path problems, which you have seen in Competitive 5, Com 2010. Now, I assume that you have done Dijkstra's algorithm before. In fact, this is the weekly exercise for you to write Dijkstra's algorithm. This is an algorithm for a single source shortest path, meaning that you find the shortest path from just one vertex to every other vertices in a graph. Now, we're going to be doing something called Bellman-Ford algorithm. I might repeat Dijkstra for quickly, just so that you remember. But we're going to be focusing on Bellman-Ford algorithm because that one can handle negative weights. And then after that, we're going to be talking about the matrix multiplication method and Floyd-Warshall algorithm, which are all pairs shortest path algorithms. So what I mean by all pairs shortest path is it's going to find the shortest path from every vertex in the graph to every other vertex in the graph at the same time, right? And you'll see that you can do this faster rather than just doing Bellman-Ford or Dijkstra on every single vertex, like one by one. So you try to find all the shortest path in the graph at the same time. Let's start with some definitions. I'm going to go over the notations that you will see this week, starting with how I define a graph. I always define a graph using GVE here. Basically, a graph to me is a set of vertices and a set of edges. And this is also how I want you to think about graphs. Think about them in terms of these two sets. We're going to use UV with round brackets to denote an edge between U and V. So if U and V are two vertices in the set of vertices. And all these other definitions you probably know. Degree is how many edges connected to the vertex. The graph can be weighted or not weighted. The graph can be directed, as in there's a direction in the edges. A graph can be acyclic. It contains no cycles. And this last one here, probably good one to talk about because sometimes people get this wrong. A graph is connected if there's a path from each vertex in the graph to every other vertex. So if you have a graph that looks like this, A, B, C, D, E, F, G, some students say these are actually 3 different graphs. No, this is just one graph which is disconnected. And you have 3 components, A, B, C, D, E, F, and just G here, the single component here. Now, that word component can also be tricky sometimes. When I talk about component, I mean connected parts of the graph. Like A, B, and C are obviously connected, D and F connected, and G is also connected. Well, because it's a single node. So I call these 3 connected. And so there are 3 different components. Component is different to subgraph though, because when you have a subgraph, you're just taking a subset of V and E, and that will form a graph on itself, right? So is ABC a subgraph? Like with all the edges here, is ABC a subgraph of the whole graph? Yes, it is. Is DEF also a subgraph? Yes, it is. Is ABC and DEF, like these 2 components together, does that form a subgraph? Yes, it does. So make sure you understand the difference between a subgraph and a component. When I think about component, again, I just think about connected things, connected parts of the graph. So I guess one way to unify that is you say that a component is a maximally connected subgraph because you can go from one vertex to every other vertex. Now, that's also another point of contention, because if I say that this component here is connected like A, B, and C, well, I can go from A to B, I can go from A to C, but I can't can't go from B to A or to C. So can you say it's connected if you can't go from B to A? Hence, there's the term weakly connected and strongly connected. So weakly connected means that, well, I guess informally there's a line between every single node in the component. So this is a weakly connected component because there's a line going from A to B. Well, there's no line going from B to A because this is a directed graph. But if you imagine this is undirected, if there's no directions on the edges, then they're connected, right? As opposed to strongly connected, where you can go from every vertex to every other vertices in the graph. So I guess if you flip D and E here, so if D can go to E, then E can go to F, and F can go to D, then that would be a strongly connected component. I'm not sure if I'm going to be using weakly connected or strongly connected anywhere else in this course, but just in case you read something and this term like shows up, well, you probably know what it's about. But also make sure you know the difference between a subgraph and component, because like I said, this is something that some people get wrong. Okay, enough on terminology. I think we can go to the actual problem. The problem that we're going to be doing today is called the maximum flow problem. And the description is actually quite simple. Suppose you want to move materials from one location to another location. So each one of these vertex, they represent a location, and each one of these edges tells you that there's a connection between the two vertices. And we want to move goods or materials from the source vertex to the sink vertex. So the source vertex produces the goods or the material, and the sink vertex consumes them. Now, the condition you must satisfy is that every other vertex can only propagate the material. So if A, B, C, or D receive N materials, they have to send out N materials as well. The source and the sink are the only exceptions, right? Source only produces and sink only takes. Now, the weight of each edges, they signify the amount of materials that you can send using that edge. And any configuration is called a flow. So for example, if I choose to send 4 materials down on this path, the green one here, I can do that because, well, this edge here, the capacity is 13. I'm sending 4 out of 13. Here, again, I'm using only 4 out of 14 available. But from D to T, I use all of them. I use all 4. Okay. So this is one flow. Is it a good one? Well, no, because you can definitely send more. You can probably send 3 more at least. You can send 7 here. 7 will have to go out here as well. But then you can send 3 up here. You can send 3 from D to B, and then the 3 can go from B to T. So you increase the flow from 4 to 7. Now, what you want to do is to find the maximum flow. So you want to find the greatest rate at which you can move materials from the source to the sink. Now, this is not as straightforward as just adding up the 16 and 13 here. So I can produce 29 from the source. I can send out 29. Well, I mean, this edge can take 16, that edge can take 13. But if I send out 29, and every other vertices can only propagate, right? If they receive 10, they have to send out 10. Then the last node here, the sink node, can only take in 24. You're gonna have like 5 missing in the system somewhere because you can send out 29, you get 24 in. So that's no good. You will break the law. The rule is that we must have S and T being the source and the sink, but everything else must only propagate. So whatever comes out of source must be the same as whatever comes in the sink. And you might think, well, that is stupid because surely if I want to, I can leave some materials in the in A, B, C, or D. Well, but that's what the problem is. It's a pretty common problem, and it can be quite complex, especially if you allow goods or material to be left over in one of the nodes, and it becomes more complicated. And we are just here to study the simplified version of it. So you can see how this is used in real life. You can use this in material distribution, like what we just talked about. But you can also use that in road networks, rail networks, even water networks, because focus here is on how much can you send through a network, like whether that be the road itself, the rail, the water pipes. Yeah, I hope you can see how this can be used in real life. It's also very well studied. We're going to be talking about Ford-Ferguson method. I should not call it algorithm. I should be calling that a method. I'll talk about that later. It's not that important. Then we're going to talk about Edmonds-Karp algorithm, which is an implementation of Ford-Ferguson method. There are also Dinnick's algorithm and KRT algorithm, but we're not going to go through that. Sorry, just keep it simple. Let's just do Ford-Ferguson. So going back to the example, just to show you that this can get a bit more complicated. We're probably going to be doing this one in the workshop. But here I have a better flow in a way, because instead of just doing 4, 4, 4, now I'm setting 12 up top as well. So now the total flow is 16. I can send out 16 from the source and I can accept 16 at the sink. And here's another one, like I said, just to show you that it can get complicated. This one is 19. I'm sending out 11 plus 8 and I'm receiving 15 plus 4. But see how the goods kind of move all around the place now. Let's look at B. See how B receives 12 and 7. So I got 19 coming in. And B is sending out 4 and 15, also 19. And that applies to every single vertex inside the graph. Well, apart from the source and the sink. This is probably a good time if you want to pause the video and try to do the problem yourself. I think it's a good practice for you to always try to do something yourself before you know how to do it properly. And here I give you 2 solutions. Well, obviously 15 is better. And then see if you can do better. Because if you try yourself, you will have some ideas running in your head on how to do it. And later on, when you see how this is actually done, well, if those ideas match, then that would be great. And you will get this aha moment when you see the actual solution, like, oh, this is how you do it. That's how you do it. You appreciate it more, basically, if you try to do this yourself first. But anyway, we're probably going to be doing this in the workshop as well. So, yeah, I think we'll do the exact same question, exact same problem, because I don't think I'm solving that one in this lecture. Anyway, if you want to pause here, go for it. Because now we're just going to talk about the formal definition of the problem. Alright, first thing first, we call our graph a flow network. So the graph here that you see is a special kind of graph. It is called a flow network. And the properties that it have to satisfy are, well, every single edge will have a non-negative capacity. And also, if you have an edge going in one direction, then you can't have another edge going in the other direction. You see that happening here. If you can go from A to B, then you're not allowed to go. You're not allowed to have an edge going from B to A. That's just the rule that we have to make this problem simple. Now, can you get around this? Yes. Basically, these are quite limiting, but you can then modify the problem to allow an edge going, well, to allow 2 edges going in 2 different directions. And of course, in the graph, in the flow network, you have a source vertex. We're going to call it S, and we have a sink vertex. We're going to call that T. We can assume that the graph is connected. Because if it's not connected, then, well, we can just ignore those nodes. And we also assume that each node is between the source and the sink. Right, this is just to make our life easier. And also, you should be able to see that the number of edges must be greater than or equal to the number of vertices minus 1. Because the graph is connected, and each vertex has to grade at least 1, so, well, this must be true. Like, if you have the number of edges exactly v minus 1, then you're just looking at a single, like, linear tree, like just a single linked list, if you like. Right? I hope you can imagine that. We define a flow to be a function from two vertices into a real number. Yeah, I wouldn't worry too much about this definition. This is the definition in the textbook as well, but it will be obvious later what a flow is. Basically, a flow is how you're using the edges in a graph. It's like how much materials are you sending on each edge in the graph. So, for example, like here are two different flows, right? The top one, you're sending 12 from S to A to B, and also B to T, and 4 on S to C, C to D, D to T. So that's different to the flow at the bottom here. And I can write these flow. Like the way I represent this flow is by using the function f. So here's a representation of the flow. As a, well, here's the graph, and here's the function. Right? It's just a function that tells you how much of the edge, of the capacity of the edge are you using. So from S to A, you're sending 11, right? So FSA is 11. From D to B, you're using 7. So FDB is 7, and so on. See how now it's just a function from the set V times the set V. Like you take two vertices and it maps to a real number. I mean, in our case here, we're just going to be using integers of real number. But that's what a flow is. And a flow must obey two rules. One is the capacity constraint. So your flow, like how much you're using in each edge, cannot exceed the capacity. Well, that's pretty obvious. And the second one, also we talked about this earlier, you have to obey the flow conservation rule. So the amount of material coming into one node must equal the amount of material coming out of it. Right? If a node accepts 10, it must also deliver 10. Okay, so that's what a flow is. And our task is to find the maximum flow. You got to find a mapping from the edges into numbers such that the value coming out of the source, which is the same as the value coming inside the sink, is maximized. And actually for this flow network here, the reason why I told you to give it a try yourself, because this is not maximized. See if you can find a better flow. Well, you can definitely find a worse flow. For example, here's a flow with value 2, because I'm only sending just like 1 from SABT and sending 1 from SCDT. But you see how this is just another mapping from the edges to R, well, to value. It's like now FSA is just 1, FAB is just 1, FDB is just 0, FBT is 1, and so on. Right, that's what a flow is. So make sure you understand what a flow is, and it'll be natural to understand what a maximum flow is. Okay. Now, as I said, the flow has a value, right? A flow network can have many flows, and each flow has its own value. So the one here, the flow value is 2. The one before, the value is 19, and you can do better than 19. So this is how we define our flow. You just add up, basically, you just add up all the edges coming out of the source vertex. Well, I guess equivalently, you can also count all the edges coming inside the sink vertex. But doesn't really matter, right? Because if you follow all the rules, and if you can send out 20 out of the source, then 20 will also go inside the sink vertex, right? If you follow the flow conservation and you follow the capacity rule. So whatever the maximum flow is, that's what we're trying to look for. So we're trying to find the largest value, like this F value. Okay, so again, give it a try. you can try using brute force. Think about how you would do this in brute force, and also confirm that greedy algorithm will not work. It's always good to do. It's always good to do those things. Like think about the brute force solution and think why greedy doesn't work. Right. So we're going to talk about the Ford Ferguson method now, and this will look cryptic to you. You will go, what on earth is this? Start by setting FUV to 0 for all pairs. Well, that's obvious. You start by not using any capacity at all. And while there's an augmenting path in the residual network GF, augment the flow F along P. Like what on earth is augmenting path? What on earth is residual network? We're gonna go through that. We're gonna talk about this definition later. But first, I think it would be easier to explain this by just going through an example. Okay. So by the way, I mentioned earlier that we call this a method, not an actual algorithm, because it's just saying you can implement Ford Ferguson method in different ways. And Edmund Carp is one implementation that uses breadth first search, BFS. This is going to be clear later, like near to the end, we'll go back to this. All right, so how does the system work? Well, let's say you have a very simple network like this. You want to send 3 F from S, and you can accept 3 in the sync, right? Pretty sure you can see. Well, I'm sure it's not too hard to work out how you can send out 3 and accept 3 from this. Actually, I'm just going to modify the capacity from C to A to 3 because I think that makes a better example. So now you have this flow network, and you got to find the maximum flow. Let's just try something. Let's just try to brute force it. Let's try to send 1 from S to A, and then I guess that A has to send 1 to T. Yep, we can do that. What else can we do? I guess we can also send 1 down to C. So we're using 1 capacity out of the 2 available, and then we send 1 from C to T. So that's the second path that we have. So see, all I'm doing here, I'm just going to find a path from S to T where there are capacities left. Are there any other paths that you can see that we can send another 1? Yeah, there's a path here going from S to C, C to A, and then E to T, A to T. So that's 2 going down to C, 1 going up to A, and then 1 going down to T. Now that should be the maximum flow because, well, we used up all the available capacity coming out of S. So S can only produce 3, and T can accept 3, so that's good. We obey the flow conservation rule, and we obey the capacity rule. So notice that all what I'm doing here is just I keep on finding a path between S and T. And this path is what we call an augmenting path. It's just a simple path from S to T. Now, I'll say here it's a simple path from S to T in the residual network GF. We still don't know what this is yet. We're going to come to that after this. But before, think about the process of choosing the augmenting path. Because it's not that simple. It's not as simple as doing, let's just choose any and be correct. No. Because if you choose SC, CA, and AT as a path, you can send 2, right? You can send 2 down to C, send 2 up to A, send 2 down to the sink. And then what? Well, you can't send the goods from S to A anymore because it's full up. Like A can only send down to T, and capacity is 2. So if I send 1 to A, well, where are you going to send the 1? You're going to break the rule of flow conservation. So you can't choose any path randomly and hope that it will give you the maximum flow because obviously it failed here. You can probably say that this is the greedy algorithm, right? Because you're choosing the edge that has capacity 2. So you need to put in a bit more effort than just choosing the path randomly. And this is where the idea of residual network comes into play. So a residual network of G is the edges of G that still have some capacity left. Now we're gonna call this GF. But I guess if you just want to see which edges in the network, in the flow network, if you have capacity left, then that's the orange ones here, right? So I have one capacity left here. I have one left here as well. I got one left there as well. Now, the thing about residual network is you also have capacity going the other way. Looks like this. Now, this looks pretty cluttered and messy, sorry. This is really something which would be easier to do on a whiteboard. So maybe you can go through this again in a workshop if you like. But the most important thing to note is that I have edges going the other way with capacity as well. So how do we use these edges? Well, they are used to cancel flow. This is why the capacity is the same with the capacity going the other way. So if I can send 2 down from S to C, then I can also cancel 2 going from C to S. That's what they're there for. So the way it works is, let's look at our predicament right here. We're stuck because we can't send something out from S to A. Okay. So we can't send anything from S to A because A to T is filled, right? And the reason why we did that, well, the reason why it's filled because we send 2 from C to A. So what we can do with this residual network is, well, you see there's an augmenting path from S to T. If I go S, A, C, T, right? That's an augmenting path. And this involves going the other way from A to C. So this is actually saying, cancel one shipment from C to A. I'll make up for it. I'll make up for it. Like the one that you need to go from A to T, I'll send it from S. So S will go to A and then go to T. That's the one deficit by canceling it. And then instead, send that one good from C to T instead. So instead of sending to A, send that down to T. So that's what I'm doing here. See, having edges going the other way allows you to cancel and redirect goods. Now, if you just look at the original graph, this is going to look a lot more simpler, right? We have like, okay, this is where we end up. So I'm just going to send one there, and that will cancel out this one, and you'll send the one from C to T, done. You have the optimal solution. Now, trying to draw the residual network in the same graph as the flow network is a bad idea. It'll get super cluttered. It'll get very messy. So what we do is we would draw a separate network, the residual network. We draw it here. Now, when you first start, the residual network is very easy because it just tells you like you just have the capacity of every edge. So I got 1 here, 3 here, 2 there, and so on. And this is how we define the residual capacity. So each edge in the residual network doesn't have capacity; it has residual capacity, and you define it like so. This is actually very simple. It's just saying that if you do have an edge going from U to V, like let's say if you have an edge going from S to A, then the capacity in your residual network is just, well, capacity of the edge minus the flow you currently have on it. So let's say C to A, right now the flow is 0. So the capacity in residual network is just 3. 3 minus 0, the current flow. If you use up one of them, then the capacity is going to be 3 minus 1, so you will have 2 here. Simple, right? If there is no edge going from C to A, well, let's say here, there's no edge going from A to C, then the residual capacity is just whatever flow you have on it. because you're not allowed to send goods from A to C normally. So right now, what's the capacity from A to C? Nothing, 0, because you can't send. There's nothing being sent from C to A, so there's nothing to cancel. Right, so that's what the second line is. So really, if you want to draw the residual network properly, this is probably what it should look like. Okay. So right now we haven't put any value at all. Like every edge in the flow network has 0 flow. So that's what the residual capacity looks like. Right, the capacity of going back is just 0. If I increase, let's say we go SAT, let's go up by 1. Okay, so here I'm using 1 out of 1, here I'm using 1 out of 2. So now from S to A, the residual capacity is now 0, but from A to S, the residual capacity is 1, because you can't cancel that one you just did. Same thing here. You can still send one more from A to T, but you can also cancel the one that you already sent from A to T. So you have one going from A to T, you also have one going from T to A. Let's do more. Let's add one. Let's use this augmenting path, and let's add one there. So now, the residual capacity going from C to A is now 2, because we used up 1, but you can't cancel 1. The residual capacity for going from A to T is 0, because you can't send in any more, but you can't cancel 2. So that's why you have 2 going the other way. And I hope you agree with me that if we just remove those edges with 0, because that doesn't do anything anyway, right? It'll just make the graph simpler. So that's what we're going to do. Here's a proper definition of residual network. A residual network of G induced by F. We say this is GF. The V is the same, the set vertices are the same, but the edges are going to be different, in where we only care about the edges where the residual capacity is greater than 0. So if the capacity is 0, don't worry about it. And I guess a way to look at it also is a residual network is just a flow network where you're allowed to have both directions. You can, if you have a flow from U to V, then you also have a residual in the residual graph, you have something from V to U as well. I'm getting tired. I can't say residual properly now. Like, please excuse me. Right. So the purpose of this residual network is to tell us how to add flow to the original flow network. And the way we do this is by finding an augmenting path in the residual network. Now, if you're trying to find a path in the original network, in the original flow network, then you can only increase the amount using in every edge. You can't cancel. This is the whole point of using of using a residual network, so that you can cancel the sending of good from one node to another node, so you can use that path for something else. This is what using the residual network allows you to do. Right? So one more time, if you're trying to find a path in the original flow network, you can only go up. Right? You can't reduce the amount of using in every edge. And if you find a path in the residual network, because they go both ways, you can actually reduce the amount that you're using in some edges, and that allows you to redirect the shipments and allows you to find a better flow. Right? So that's what we're going to do. And we said that we're going to augment a flow F in G when we're doing this. So we're finding an augmenting path in the residual network GF, and then we use that to augment the flow F in G, the regional flow that we have. Remember, don't think about a flow as just one path. So you're not augmenting one path. You're not improving just one path. You're improving the flow as a whole. You're improving how you're using every edge in the graph, because that's what a flow is. A flow is a function that tells you how much are you using in each edge in the flow network. Okay, so as an example here, let's say we're up to this stage when we're sending one from S to A, sending one from S to C. As you can see, we can improve this by sending another one from S to C and C to T. So this is your flow. This is the flow we have so far. And we're going to augment that flow. We're going to improve that flow. That's the lingo that we're using, right? So a flow, again, a flow is not just one path. Flow is a flow of a graph, is how you're using every single edge. So that is the corresponding residual network. And now let's go find an augmenting path. And here, there's one there. It's a simple path from S to T. That's actually the only one, because that's the only arrow going from C to T there. Like you can't use A to T because it's full up. And then from there, we're going to use this path, this augmenting path. We're going to use that to improve the flow in the original graph, in the flow network. How? Well, simply you just add the one to the edges which are highlighted. You add one here from S to C, you add one from C to T. That's it. Now, I also say here that the augmenting path is basic of flow in GF. Not sure how important this is. Well, it's technical, it's formal, it's nice. And this is how they do it in textbook. But if you don't understand this notation here, don't worry too much about it. So basically, the augmenting path, this green path here, this is a flow in the residual network. So that's what we're doing. We're trying to find a flow in the residual network. And then we're using that flow in the residual network to improve the flow that we have. Because this flow will have a value. So if I have flow here, how much can I improve the flow in our flow network? Well, by the value. And what is the value? Well, sorry, it's actually here. Well, the value is the minimum capacity that you have in the path in the residual network. So if you find a path, right? It's just the same like how we do in flow network. If you find a path, then the amount of goods you can send through that path is the minimum value in, well, one of the edges in the path, because that's the maximum that you can send. And this is how we augment the path in our original network. You have FUV plus FBUV. So basically, if the direction of the edge in the augmenting path is the same with direction of the edge in your original network, then you just increase it by one. Well, increase by whatever value is. But if the direction is different, then you actually reduce it, because this is cancellation. Okay. You're canceling. You're sending like X amount of goods from A to B, but in the residual network, the augmenting path actually goes from B to A. That means you have to reduce the amount of goods you're sending from A to B. So that is what this function f up arrow fp is doing. You're augmenting the flow in your flow network by the flow that you found in the residual network. I think the concept is actually pretty simple. It's just that this formality, this mathematics, they may turn some of you off. You don't have to worry too much about it. I'm not going to ask you anything in details about this. As long as you understand how the algorithm works, that should be enough. If you are interested in knowing more, if you're okay with this level of formality, you can go to the textbook in these pages. You can read more about it for sure. Then you will see some like rigorous proof on why the algorithm is correct. Why does it work and stuff. All right, so maybe one more example. This is the same situation that we had earlier when we got stuck. So in a way, you've already seen this. Okay, so formally, here's the residual network. What can I do here? I'm going to find a path from S to T. I'm going to find an augmenting path. Okay, there you go. There's my augmenting path. It goes from SACT. What is the value of this flow? 1, because that's a minimum in each one of these edges. Like you got 1 here, you got 2 here, you got 1. So the minimum value is 1. That's the value of the flow in GF. And we're going to use that to augment the flow in G. How do we do that? Well, if it's in the same direction, we just increase it. So here's a 0, it becomes a 1. This one is in a different direction. So we actually decrease the flow from C to A. We decrease that. And again, C to T is in the same direction. We increase that by 1. So we update that. And we also update our residual network. See now the capacity from S to A goes the other way. As in you can cancel one from A to S now. Okay. Now, can you find another augmenting path here? No, you can't. At least you can look at T and all the errors are going the other way. So that's it, you're done. All right. So again, I think the algorithm is quite simple. I hope you can understand it now. Like, look at the method here. Start by setting FUV to be 0. Well, that's a given. And then while there's an augmenting path in the residual network, so you need to know how to draw the residual network. And as long as there's an augmenting path, well, you use that augmenting path to augment the flow along P. So you get that path and you transfer it to the original flow network. Well, augmented transfer. I don't know what's a good word to say, but you understand what's going on. You don't need to care about the proof of correctness for this course. It definitely is not simple. It's called the max flow min cut theorem. It's gonna take a long time if I try to explain that, and I'm not sure how much value you're gonna get out of it. But if you are interested, if you plan to do more like theoretical computer science stuff, then yeah, this is something you can look at. You know how this works, and you can also see how it's proven to work. Anyway, final words, I guess. Yeah, this is the rundown of the method. Maybe something more detailed than just this like 2-line here. So you set the flow to 0 for all edges, make the residual network GF, and while there's a simple path, set the value to be the minimum in that simple path, and then for each edge, just augment it. That's it. Now, finally, is this the final slide? Oh, okay, second last slide. All right, just one more time. This is just a method. I mean, sorry, I called it algorithm a few times, but actually this is just a method because we didn't actually discuss how to find the augmenting path. I just tell you that the way this works is by you making the residual network and then you find an augmenting path. The reason why this is only called a method is because you can have many ways that you can implement to find the augmenting path. One of the algorithm is called the Edmond-Cup algorithm. It actually uses BFS to find the augmenting path. And there's a proof that you can do this in VE squared. You don't have to know about it again, just saying. You can also do this using Dinnick's algorithm in V squared E. They also use BFS in a different way. But yeah, just saying why this is called a method and not an algorithm, because it's just an idea. Look, here's a flow network. Here's a residual network. Go find an augmenting path in the residual network. How you do it, up to you. And then use that to augment the original flow the flow in the original network. That's all. Okay, so depending on how you find this augmenting path, well, that will be different algorithms. All right, so I found that one to be a hard lecture to explain using just a video, because usually I want this to be a lot more interactive. So we'll definitely do this in a workshop. But before that, maybe you can give this a try. Just apply the same algorithm. It's not a hard algorithm, right? You just draw the residual network. You go find a path. And you can also imagine how to do that using BFS if you like, because that would be the Edmond-Cup algorithm. So think about how to do that using BFS, find the augmenting path, and then use that to improve the flow. And you keep on doing this until you can't find any more augmenting path. So try to give it a go, and then we can discuss it more in the workshop. All right? Cool. I'll see you in the next video.